All right, guys. So then let's talk about what K is telling us here. It tells us the extent to which a reaction will proceed, right? So a big K means it's product favored, a little k means it's reactant favored, right? But it also allows us to predict the reaction, the direction a reaction is going to go to achieve equilibrium, okay? And we're going to talk about that. That's the last thing we're going to talk about today. And as we just did, we can calculate the concentrations of reactants and products when equilibrium has been reached, right? That's what we're going to talk about in next lecture, which is how do we use K to get equilibrium concentrations, right? To do that, you got to know initials, but that'll be a next lecture thing. What we're going to focus on the end of this lecture is how we can use K to do predictions, okay? So how we use K to do these predictions is we need to sort of compare the relationship of K, which is the relationship at equilibrium, to the initial conditions. Now, this can't be K, right? Because it's initial, and K specifically says it's at equilibrium. But what we can do is we can derive a ratio that is the exact same concept. It's concentration of products over concentration of reactants. It's just that we're not going to specify that this new ratio is at equilibrium. And we call this new relationship the reaction quotient. And it's a capital Q. And look at the setup on the slide. It is the exact same thing we've been talking about, right? It's just that Q does not have to be K. Now, Q could equal K, and if it does, that means you're at equilibrium, right? But Q could be less than K, Q could be greater than K, right? There's weird scenarios where Q could be 0 or undefined, right? We're not really going to get into that. You don't have to worry too much about that. But the main thing I want you to get is what starts on the next slide, which is the three scenarios of what happens when Q is less than K, greater than K, or equal to K. What does that mean, and how can I use that to predict the direction in which a reaction will proceed? All right, so we're going to compare QC to KC, and we're going to compare QP to KP, right? So the first thing is the easiest thing, right? If Q is equal to K, then what does that mean? That means you're already at equilibrium. This reaction is not going to proceed in either direction because you're already there, right? But what about if Q is less than K, right? If Q is less than K, if Q is a small number, then that means it mostly has reactants, right? Because remember, it's products over reactants. And if you're taking a small number and dividing it by a big number, meaning you have mostly reactants, that's going to be a small number, right? But if K is getting bigger, then what's happening? That means your numerator is going up and your denominator is going down. So if Q is less than K, then the equilibrium is going to shift to the right towards the production of more products. So if Q is greater than K, then it's the exact opposite, right? It's going to shift towards the left, towards the production of more reactants. Because if Q is the bigger number, then you're already starting with a lot of product, right? So if K is smaller than Q, then it has less product. It has less numerator, which means it's going to have more reactants, which means it's proceeding in the left direction. And I put this slide in there, and it basically says everything I just said, but in a more specific word form, and I wanted you to have it for your notes. So I'm not necessarily going to talk through this slide, but like I said, I wanted you to have it so that, you know, you have this to reference as you're trying to study and write notes. Okay, but we've already talked about all this stuff. So the only thing we have left for today's lecture is we need to work this example, okay? So I'm going to end this video now, and we're going to have one more short video that I'm going to use my phone with, and we're going to work out this example, and then that's going to be it for today. Okay? All right, I'll see you in the last video.